Hello, everyone. We welcome all the participants. I see that many people are still joining very timely. Let me start so that we can start without further ado. My name is Jadwiga Najder. I am Science and Outreach Manager at European Nuclear Society. And it is our pleasure to welcome two wonderful speakers to tell us more about Fukushima 15 years on. As you may know, this week we have seen two significant events for nuclear energy. First one of them, which happened earlier in the week on Tuesday, was Nuclear Energy Summit, where 40 countries were talking about their plans for nuclear energy. Some countries announced embarking into nuclear sector. European Union announced its SMR strategy, and among others, Japan recalled its strategy of energy security, safety, and reliability, as well as reminded the interest in restarting the existing power plants and also developing the new generation of reactors. But this was not the case 15 years ago, when Japan suffered a natural disaster, which then resulted in an accident in Fukushima Daiichi power plant. And this anniversary of 15 years was just this Wednesday. And since then, many lessons were learned and many innovations were implemented in different disciplines of nuclear energy. So two of our experts today will speak about that. Uwe Stoll, who is a technical chief advisor for nuclear facilities at Framatome, and Ryunosuke Kashiwaya, international relations coordinator at TEPCO. And we also have TEPCO colleagues joining to answer questions if necessary. So I will invite first Uwe Stoll to tell us about the lessons learned on safety, in particular in Europe. Uwe, the floor is yours.
Okay, thank you very much. So I will share my screen and hopefully it will work. Could you see it?
It works.
Okay.
Just about right.
So let's talk. I will a little bit remember what happened in 2011. Then one of the things we have learned new terminology after the Fukushima event, and it's only one slide, but with new phrases. And then I will go over the requirements coming from different levels, from the agency inside the EU. And the last one is how these requirements were transported in real things, real equipment, real systems that were introduced in the nuclear power plants. Let's start. What happens in 2011? Short to remember about Fukushima nuclear power plant. It's Fukushima Daiichi. I hopefully write it right, because there's a second one around 6 to 7 kilometers from that. It's Fukushima Daini. But Daiichi nuclear power plant with 6 units. You see some points here. There are different stages. 3 of the units were in operation. Unit 1 to 3, 4, 5, and 6 were an outage. There was a special one, but in Unit 4 there was an inspection of the reactor pressure vessel. There was no fuel inside the reactor. On the picture we can't see the Unit 5 and 6. They are a little bit right of the picture. So sorry for this one. I don't have it in English, so I use the German one that explains what happens. You see on the top how it's the plant located, the reactor building, the turbine island, the cooling water pumps, and 0, this means normal level. The requirements in Japan for Fukushima design, for tsunami design for the Fukushima site was 5.7 meters. There was a wall about 6.3 meters, but the real tsunami, what happens was 14 meters. So we get the flooding of all the cooling pumps. We get the flooding of the turbine island where the emergency diesel generator were located. And we get a lot of destruction in the switch gears and so on. So now a little bit more in detail, not too much. It starts everything with an earthquake on the 11th of March, 1446, in a magnitude of 9. This was the biggest earthquake what we have recorded in Japan until now. The power grid in northern Japan collapsed, not completely. Daini had one of the lines available, but was good for the plant. But everything in the plant works well. So there was a start of emergency diesel generators, and everything works normally from all what we're knowing today. Around 1 hour later, a tsunami, and we talk about tsunami, in reality, it was 3 waves, reaches the plant with a real high of 14 meters, as I have seen. The flooding of the plant area, and we lost the emergency diesel generators. We lost the cooling water. We lost the electricity supply. So it was a complete station blackout. But there were some passive systems in the plant that at the beginning makes available the cooling of the core. But also this passive system were lost in the unit 1, 11th of March, and the other one a little bit later or 2 days later. And in this case, the plant is so designed that the heat transfer goes via the safety valves into the condensation chamber, by this way. But when you make this type of cooling, you are losing the level in the reactor, and sometimes you have no more water in the core, and the core starts to melt. So this was stopped by the team on site with seawater injection. But what we have was several hours of not cooling the core, that at the end leads to core melt. I come later a little bit more to. And due to the fact that we injected all the heat inside the so-called primary containment, so the pressure inside this primary containment goes up above the design pressure, and there was leakages in this primary containment. And with these leakages, the hydrogen that comes from the water second reaction comes into the building around. And at the end, we have seen hydrogen explosion in unit 1 and 2, and also in unit 4, where no fuel was in the reactor. But exploded was not the containment, exploded was the building around. So this was at the end the situation what we have at the 15th of March 2011. You see the unit 1 destroyed by the building with hydrogen explosion, the unit 3 heavily destroyed, and even the unit 4. It was a big question today. The explanation for that is you see here a common stack with connection to unit 3 and 4. And the hydrogen comes via disconnection from unit 3 and unit 4, and at the end leads to an explosion of unit 4. Unit 2 was no explosion due to the fact that with explosion of unit 1, there was a hole in the building, and due to this hole, there was no accumulation of hydrogen to an extent that leads to an explosion. So this is the situation what we have seen 15th of March 2011. What we know today about the fuel is in unit 1, what was 28 hours without any cooling. Most of the fuel is no more in the reactor, but is inside the containment, has destroyed even the concrete, but has not gone via the primary containment. Unit 2, there is more fuel still in the reactor, but there's also some fuel in the containment, but no destroying of concrete. And unit 3 is something between unit 1 and 2. So this what we have seen on site, and what starts afterwards in all the countries, in all the international organizations, starts and look into the lessons learned. First of all, I would say I have for me, special two lessons learned. The first of all, it's passive system, not overall health against everything. There was passive system, but they also failed after a certain period of time. So passive system, when I hear sometimes today we have only passive system, it's not the final solution for safety. The second one, and this is more also for interest for a lot of people, is Fukushima have fulfilled the Japanese regulations for tsunami. So, and then I had some discussion about how is defined safety. And what I have learned from one of the leading European regulators saying, I will give a license not because the plant is safe, but because the plant is fulfilling requirements. For the safety itself is it's the operator is responsible. It's interesting lessons learned, because how often is used to frame my plant is safe because it fulfilled the requirements. And this, my personal lessons learned for this one. It's not because it fulfills the requirement, the plant is safe. So we have to think about the safety. But there were introduced some new words. First of all was robustness. Huh? What is robustness? In the frame of nuclear power plant, it means you have a design requirement, and what happens if the conditions are higher as by the requirements. If the earthquake is bigger, the flood is higher, or the aircraft, what you have designed against, is bigger when it flies into a nuclear power plant. So, but it also includes questions about when you have prolonged power supply failure. So you have for several days no power, external power. When you have no access because the only road that exists is lost. How we are prepared for that. This calls robustness. And in many parts of the world, a so-called stress test was made and looked what happens if we're going to beyond design events. What I include, as we have seen in Fukushima, the earthquake was higher and the tsunami was higher as required by the design. And there was another word called cliff edge effect, is that it describes a sudden drastic shift triggered by a small change, typical when a critical threshold is crossed. And the question here was how close a cliff edge is to the design. Very easy example, your plant is designed for flooding of 4 meters. What happens if the flooding is 4 meters and 5 centimeters? You have lost all the safety systems and so on. And from today's point of view, this is critical because the cliff edge is too close to your safety limit. So this means cliff edge effect. And in the last, I would say 2 to 3 years, a new word comes up in the nuclear safety discussion is so-called resilience. Resilience means in the field of nuclear safety and emergency management as a social technical system's ability to effectively adapt to an array of abnormal, downgraded, and critical situations. What it means when we talk about robustness, we're discussing nevertheless about things what we knowing. We are discussing about earthquake. We are discussing about the tsunami. Resilience is looked on things what we don't know today. How we are prepared for things that we don't know today. This is a discussion just starts in the agency, and I expected there will in short time some papers about this new point. That is one of the lessons learned from Fukushima. So let's go to the different things, what happens and what are new requirements coming up after the Fukushima accident. Even in 2011, the agency drew up an action plan to improve the safety worldwide. And there was requested the timely assessment of protection of nuclear power plants against beyond design basis natural hazard. There was requested improvement of emergency preparedness. And one of the non-technical requirements was the request to ensuring an independent and effective state supervision. For this reason, in Japan, we have now the so-called NRA, Nuclear Regulator Agency, but there was also changes in some other states, not only in Japan. In 2012, there was a special conference of the Convention of Nuclear Safety. And here again was somehow, they have not called it a stress test, but every member of the CNS was requested to submit a national report describing the safety of the nuclear power plants. And then these reports were discussed in the conference. And in addition to plant-specific recommendation, there was some generic recommendation with organizational factors, off-site emergency protection, and international cooperation. And you know the agency is typically working with safety standards. And 5 of safety standards were adapted, and there was the so-called Vienna Declaration made in 2015 with some requirements that we have today. So the first one is new nuclear power plants must be planned and built in such a way that severe accidents are prevented. Nevertheless, in the event of severe accident with possible release of radionuclides, there must be no long-term contamination outside the plant. Sufficient time must be available for protective measures of off-site emergency response. Clearly, when you read this one, clearly outcome of the lessons learned from Fukushima. For the existing nuclear power plants, safety must be regularly reviewed and improved. Question is really every 10 years, periodic safety review have to be made for the existing plants, not only looking inside the plant, but looking also outside the plant. One of the example is when there was made the stress test, the people looked in the design or design requirements, what they have, and typical about flooding. And then there were some plants located on the river. And after the building of the plant, there was building a dam a little bit higher at the river. And there was not looked in what happens if this dam breaks and you get a higher flooding. So this means also by safety review, it's not something only internal in the plant, but it's also looking on the external preconditions you have for the site. The next one in this Wiener Declaration was national regulatory framework should ensure that these objective and must take into account the safety standards of the agency, and there is the review every 3 years by CNS. And 5 safety standards were adapted, and on the safety demonstration, all in the framework of lessons learned from the accident in Fukushima Daiichi. So now coming to the level of the European Union. In 2011, the responsible Energy Commissioner requested a stress test for all 143 nuclear power plants in Europe. So the European Nuclear Safety Regulators Group, called ENSREG, defined the scope of the test, and the member states write a report about the safety of their things. That was, again, a stress test, so looking what happens in the power plant. First of all, if the external event is higher as in the design, and is there some changes in the precondition of the site, as I explained, for instance, with an additional dam in the river. This was published in a report called Compilation of Recommendation and Suggestion from the Review of the European Stress Test. There was made a directive from Euratom, again, with practical the same, the strengthening of national supervisory authority, the anchoring of the defense in depth concept, what was not so new, but it was more deeply defined, the performance periodic safety review at last every 10 years, and the performance of a thematic peer review at European level every 6 years. The last one was on fire protection of this thematic peer review. The first one afterwards was aging. So we have now had 2 of these peer reviews. There exists another organization called WENRA. It stands for Western European Nuclear Regulator Association, but it's today more or less a worldwide association of regulators. And There were also some requests, and you can find the same things as I mentioned before, is the requirement to consider national hazards beyond the design limits and the requirements for preventive and mitigate measures and equipment for the control of beyond design-based accidents were fundamentally revised. So there was a lot of new requirements right in this one. And now coming to what happens in the nuclear power plant. Practically every plant in Europe and in the world has looked on upgrades to improve the situation for longer power outages, for natural disasters, for severe accidents. And this is not only something inside the plant. I know some plant in the world they have looked on, and there was only one road to access the power plant, and there was typical after heavy rain land slippery, but there was no access to the power plant via this road, and they created the possibility that the people can go by ship to the power plant. But a lot of things were made inside the power plants. The first of all, emergency power supply. In many plants, mobile equipment was added to the equipment, but it's not only the mobile equipment, it's not only the mobile emergency diesel generator, but there was also created the access point. It doesn't help you so much as a diesel generator when you have no plug where you can connect it to the plant. So this was a system. It's not only diesel generators, these were mobile pumps to get the possibility to pump even when you lost all the energy for a longer period. But means also cooling capabilities, structural protection. In many cases, they were increasing in dams, for instance, because they have now found the flooding could be higher as it was seen. We have seen this question about containment venting. What was made in Fukushima a little bit late because there was the procedure that first of all there should be an official okay from I don't know, but it was not a decision by the plant. Final decision comes from politics when you can make this venting, and a lot of plant afterwards make an upgrade and install the filtered containment venting that you can reduce the pressure without giving too much radioactivity to the environment. Hydrogen management, in many cases, there was added passive autolytic recombiners, as you can see here, to reduce the hydrogen and to avoid hydrogen explosion. But there was also increased emergency preparedness. This is sometimes not only on each and every unit. In France, for instance, there was organized 5 centers where a lot of mobile equipment was localized. But not on each and every plant, but it was possible and organized to bring this very fast to a plant in emergency. This is what I mean with emergency preparedness. And there were also adapted operating procedures. Not every plant until 2011 had so-called severe accident management guidelines. And many of the plants added now the severe accident management guidelines, what I would express today, but all the plants what I know have no guidelines how to deal with a severe accident. Looking into account with all the things we discussed as lessons learned, you can have a higher impact for an external event. You can have a longer loss of electricity. You have to organize maybe born in a pressurized water reactor to keep subcriticality. And one point not mentioned until now was there was a lot of discussion about the fuel pools. No? There was an expectation that the core melt in the fuel pool in Unit 4 due to the fact that there was fresh unloaded fuel in the pool. And a lot of things were done around safe cooling of the fuel pool. And the last picture I would show to go over to the Japanese colleagues in 2022. I was invited by the NIA in the framework OECD NIA to Fukushima site. This is a picture of what is made, I think, nearly here. You can locate it by the picture because in this time there was finishing the new construction for the fuel removing at Unit 2 and start of construction of the new confinement of Unit 1. And I will stop here and now give over to my colleagues from TEPCO.
Thank you very much, Uwe. I remind our participants that you have the opportunity to write your questions in the chat, and we will cover those questions after the second presentation. So don't hesitate to tell us what are you missing or what you don't know still while the presentations are being done, so that this is not forgotten. And now I will give the floor to Ryunosuke Kashiwaya, who will tell us about the most recent actions on site of Fukushima Daiichi and all the different innovations that were implemented to make this possible, as well as different simulations of alternative scenarios that were done. And finally, we will hear also what is Japan doing right now in the nuclear energy sector. So Kashiwaya-san, it's to you. I welcome you to share your presentation as well.
Oh, okay. Thank you for your introducing. Can you see my presentation?
Yes, we do see it.
Thank you. Okay. Hello, everyone. I'm Ryunosuke Kashiwaya from TEPCO.
Excuse me. Sorry, maybe you can put it in the sharing. Exactly. Thank you.
Okay.
Yes. Thank you.
Okay. Thank you for giving me the opportunity to share the current status of Fukushima Daiichi cleanup and Japan's nuclear energy landscape with you. First of all, as Mr. Ube-san kindly explained earlier, a melt slumping of a reactor core occurred in Units 1 to 3 of the Fukushima Daiichi nuclear power station during the 2011 Fukushima accident. For 15 years after the accident, we have been working on decommissioning to minimize the risk posed by radioactive materials. This slide shows 5 major activities to address different sources of risk. In the early stages, most efforts were devoted to addressing the issue of contaminated water management. Today, the situation has significantly improved, and the discharge of ALPS treated water began 3 years ago. In addition, the spent fuel stored in the fuel pools of the accident-affected units had to be removed. We expect to complete the work by the early 2030s. Given this background, attention is now turning to the even more challenging task of retrieving the molten fuel debris. And now I'd like to go through these topics. The first topic is spent fuel removal. Spent fuel is stored in pools at the top of the reactor buildings, and its removal is a critical task to reduce the risk of radioactive material being released in surrounding areas. As you can see in the pictures, we built the structures covering each unit for the spent fuel removal work and to prevent dust dispersion. Following the completion of fuel removal from Units 4 and 3, we are now preparing for fuel removal for Unit 1 and 2. We plan to begin the work on Unit 2 by June this year. Overall, fuel removal from all units is expected to be completed in the early 2030s. Next, I'd like to touch on the fuel level retrieval. As shown here, Each unit has different condition of the reactor damage and the estimated location of the fuel debris. Various internal investigations and analyses conducted so far have helped us understand the reactor condition and location of the fuel debris. Today, I would like to focus on two of our achievements. The PCV, primary containment vessel internal investigation at Unit 1, and the trial fuel debris retrievals conducted at Unit 2. I will start from Unit 1 investigation result. In 2023, we inspected the lower section of the pedestal inside Unit 1's reactor pressure vessel using a remotely operated vehicle. We call it ROV. As you can see in the upper left picture, the ROV enters the pedestal through an existing opening. The images captured during this investigation are shown on this slide. From the image on the upper right, we identified shelf-like deposits located roughly 1 meter above the pedestal floor. Below this area, part of the concrete at the base is missing, and the levers are exposing. We also confirmed that deposits nearly 1 meter in height cover the entire floor, and that part of the upper structures had fallen. Two images at the bottom of the slide were taken near the pedestal opening, from both the inside and the outside. From the inside image on the bottom of left, we assessed that there is no noticeable deflection or deformation of the levers or the inner skirts. From the outside image, within the area observed, only a limited amount of concrete is lost on the outer wall. Following the results of our investigation, we conducted impact assessments. This slide presents a summary of the assessments regarding PCV. We cannot rule out the possibility that losing the pedestal concrete could weaken the structure and cause the RPV to subside in the event of an earthquake. However, it is unlikely that this would cause major damage. We also assume that only a very small amount of dust would be generated in this case. Therefore, our assessment concluded that there would be no impact on the environment. Additionally, since the horizontal movement of the RPV is limited by surrounding structures, we predict that there would only be limited slanting. Slanting refers to a condition in which the RPV becomes severely tilted, resulting in significant damage to the PCV and itself. Therefore, our assessment has concluded that even if there was an impact on the RPV, there would be no impact on the PCV, and a containment function would be maintained. We also ran an exposure impact simulation. Two main assumptions of the scenario are RPV subsides 1.3 meter, and a large opening was created in the PCV. Even in this case, the exposure that at the site boundary would be a maximum of 0.04 millisievert. This means that the exposure risks to the surrounding environment would be extremely small. And now I'd like to talk about our current fuel debris trial retrieval at Unit 2. This trial retrieval at Unit 2 turned out to be an important milestone for advancing our decommissioning process. As you can see in this slide, a telescopic arm was inserted from outside the PCV. The retrieval tool was lowered by wire, like a fishing rod, to pick up and collect the debris. We successfully conducted these operations in 2024 and 2025. And the collected samples are currently being analyzed using various methods. We are learning a lot of information from these analysis results. Today, I have very limited time to introduce all of our achievements. But we have a dedicated website called Fuel Debris Portal Site, which has lots of visual information and data regarding fuel debris retrieval activities, such as our strategy, the current status of each unit, and detailed information on fuel debris analysis. If you are interested, please scan the QR code or visit our website for more information. Now, let me move on to the next topic, water management and discharge of Alps treated water. Before discussing the Alps treated water, let me explain the mechanism behind contaminated water generation. As shown the bottom left, we have a water circulation system to cool fuel debris in the PCVs, which mixes with radioactive materials, resulting in contaminated water. Additionally, groundwater and rainwater entering the reactor buildings become contaminated, eventually generating surplus contaminated water. After the concentrations of cesium and strontium are reduced by filtering equipment illustrated here, the multi-nuclide removal facility, we call it ALPS, removes most of the remaining radioactive materials except for treating. After that, the water is diluted with a large volume of seawater. And the detailed analysis are conducted to confirm that it meets the government standards for environmental discharge. This table shows the data for 17 batches of Alps treated water discharge that have been discharged so far. The total volume of Alps treated water discharged in these batches is approximately 13,000 cubic meters on a per dilution basis. 130 cubic meters. Sorry. And the amount of tritium discharged has reached 31.2 trillion becquerel. As of now, the storage of volume, the treated water, has been reduced by 6% compared with the volume at the start of discharge in August 2023. This slide shows an example of how we assess the marine environmental impact at each location. As you can see, tritium concentrations are well below the safety standards set by WHO, the Japanese government, and TEPCO, demonstrating that the discharge procedures are being properly implemented. In addition, officials from the IAEA stationed at the Fukushima Daiichi they monitored the marine environment and confirmed that the discharge are being carried out appropriately. We have been aligned with the IAEA, hosting its task force at our site 5 times since the discharge began. These review reports have consistently concluded that it did not identify any inconsistencies with the requirements of the relevant international safety standards. A detail around water treatment and ALPS treated water discharge is available at our ALPS treated water portal site. You can find information on discharge data, including storage, nuclear analysis, and sea monitoring results. Please have a look if you are interested. Next, I'd like to talk the Japan's nuclear energy landscape after the Fukushima Daiichi accident. On this page, I have summarized the major changes that took place in Japan's nuclear energy sector after the accident. In the Japan's National Strategic Energy Plan, revised after the accident, the government stated that Japan would reduce dependence on nuclear power as much as possible. In parallel, regulations concerning nuclear safety became significantly stricter. Two symbolic developments in this movement were the establishment of the Nuclear Regulation Authority, NRA, and the introducing of new regulatory requirements. From the next page onwards, I will explain what the new regulatory requirements and how TEPCO has addressed these requirements. A lesson learned from the Fukushima Daiichi accident is all safety functions were lost simultaneously due to the earthquake and tsunami. Moreover, the initial impact spreads and the crisis eventually developed into a severe accident. In new regulatory requirements, based on the concept of defense in depth, the design basis for and countermeasures against natural phenomena are significantly enhanced in order to prevent simultaneous loss of safety functions due to common causes. It also includes strengthened measures to prevent or respond to acts of terrorism. To comply with the new regulatory requirements, multiple measures have been reflected at Kashiwazaki Kariwa site, which is TEPCO's another nuclear power station in Niigata Prefecture. To prevent the severe accident, the new seawall and watertight doors are installed to protect the facilities from tsunami. We prepared multiple backup options to ensure cooling capability could maintain during the loss of power supply, such as batteries and mobile generator, and also ponds to store cooling water. The vent system is also installed to mitigate the impact of the radioactive material to be released to the environment. We completed the safety enhancement work for Unit 6 in May last year, and we are continuing the construction for Unit 7 as well. On this February 9th, we withdraw the control rods of Unit 6 and restart up the reactor once again. We are now proceeding with a verification of the plant's integrity under actual operating conditions, while cooperating with the inspections conducted by the NRA. This is the first operation in approximately 14 years after the accident. We will carefully and systematically confirm the soundness of each plant system. If any issues findings arise, we will respond appropriately. We will also continue to communicate the status of each startup process in a transparent and timely. This page shows the operational status of nuclear power plants in Japan. On the previous page, on the bottom sentence, I mentioned that Japan's National Strategic Energy Plan formulated after the Fukushima accident stated that Japan would reduce dependence on nuclear power as much as possible. However, in the 2025 revision, this wording was removed, and the outlook now indicates that nuclear power will account for roughly 20% of the Japan's energy mix by 2040. In this context, as the company responsible for the Fukushima accident, we are committed to applying the lessons learned and continuously enhancing the safety at all of our nuclear power stations. We will continue to demonstrate through our actions and safe operations that safety remains our highest priority. Thank you.
Thank you very much, Kashiwaya-san. We do have a whole list of questions already, and I invite you to add yours as well to the chat, following those last stories also about the Japanese energy system, the Kashiwazaki Kariwa restart and others. Mr. Kashiwaya, you can stop sharing right now. We will go to the questions, and I will read them for you, so don't worry about that. So we can start from the person who was the quickest. We have a question from Alexander Mazurok, ES Group, asking about the management of large volumes of radioactive water that would be potentially generated by a severe accident similar to the Japanese case. Without an ocean, it would be difficult to replicate the approach. So what could be the approach here? I guess this is the question to Uwe, and here is the example from Ukraine, where there was a proposition of containing water in containment with additional long-term cooling system. Uwe, do you have a comment to that?
First of all, as explained by the colleagues from TEPCO, this is a very special situation in Japan due to the fact that we had the leakages in the primary containment. So, and we get every day, at the beginning it was 500 tons per day. Today it's around 70 tons per day, as far as I know, additional water that comes into the containments and then activated with materials from the molten core and then goes via the turbine building in the tanks. So we added every day 70 tons today. At the beginning it was 500 tons by rain and by groundwater. And due to the defects in the primary containment, we get this additional water. And this is the reason why we have so much water. In other power plants not designed in this way, I do not expect, first of all, to have such amount of water. What will be happen, because even the primary containment, secondary containment, it will not so much water to be stored externally, because we don't have all this waste outside like we are now having in Fukushima. The other thing, it's right in the containment of a pressurized water reactor, what's completely different constructed. You can store a lot of water. What is even the modern concept of all this modern pressurized water reactor, where you have a so-called IRWST, internal water storage tank. So you have all the water at the beginning in the containment, and then you can add it there. So this is the modern design. Nevertheless, it was discussed to be prepared to store additional water, because as we see it in Japan, it took some time to make it so clean that you can release it to the environment. But one of the point what is discussed, to use the possibility you have inside the containment or inside the condensers, what is also a large volume what you can use.
Thank you very much for this precision. We see that there are several pathways for that. There was a question about the case of Zaporizhzhia, which I think was answered. And Matthew, please precise if you would like more answer from the speakers. We can continue to the question from Stefano Monti about him understanding that Fukushima Daiichi was testing MOX assemblies in the core. Or in the course, what could be the impact? Was there any impact on the accident evolution and on the remediation process?
Sorry, could you repeat the question again? I couldn't
Yes.
follow that.
Yes, no worries. So there is an understanding that in Fukushima Daiichi, there was ongoing testing of the MOX, so the reprocessed fuel assemblies. And would this have had an impact on the accident evolution and then on the remediation process?
So,
This is a pretty particular question. In case this is not the time to answer, we can also come back in the via emails.
yeah,
I think
maybe
there will be no much consequence difference between what's MOX fuel inserted reactor and normal uranium enriched fuel reactor. So I think, of course, the MOX fuel is plutonium included. So that's why it's but of course, after irradiation, fresh fuel generates plutonium too. So that's why from both of the reactor, plutonium has been released to some extent, has been detected in the aftermath of the accident. But as for their behavior in such an accidental condition is, of course, precisely different, but both are reviewed by safety requirement before the accident status, and both satisfied the certain necessary leads to fuel performance. So I think no much apparent different. Unit 3 had the MOX fuel at that time, but that was different from Unit 2. Unit 3 was MOX fuel. That's why such a thing hasn't been clearly detected.
Thank you very much, Mr. Ihara, for precision. We hope that this question was answered as expected. If not, please come back in the comments. We can continue to the question about whether there is a chemophysical explanation for the concrete damages observed, and here particularly about the concrete disappearance. Uwe, you're smiling.
So
is there?
I explained. I tried. So as I write that, there is no at the moment no clear answer as far as I know. There is some expert explaining us with spelling. I'm not completely convinced about that, but I have no seen other theory about the things what happens with the concrete. At least what we could say, we have not seen in all the tests and experiments were done before with core melt and concrete interaction. There were a lot of tests in the world, but this picture we never have seen before. And for this, it was a big surprise in 23 when we have seen this picture, and then starts discussion. Again, some experts are telling me it's spelling, but other experts say we do not agree because otherwise we have to find bigger parts of concrete and we doesn't find it. So it's not, I cannot answer.
I will supplement from TEPCO. As Mr. Kashiwaya explained in the slide, the photo taken so far is only where we could investigate it so far. So there's many of the area which we couldn't investigate yet. So that's why we need to continue the internal investigation and get more information as much as possible to solve what is happening, what has happened, and what is the real current situation, and that will lead to the appropriate planning and considering the technology for the field debris retrieval. So yes.
Mm-hmm. Thank you. So this is indeed a curious situation, and let's see what are the evolutions of your investigation. We have next double question to colleagues from TEPCO, from Samuel Yongkian On. Question number one: how is the TEPCO or Japanese government funding the decommissioning and dismantling work? Maybe we start from this one.
You mean the funding?
Yes. What are the funding sources for the decommissioning and dismantling?
So there's an organization called NDF, which how should I say? なんだっけ? Apologies, I forgot the English name of NDF. But so
nuclear damage compensation and decommissioning facilitation.
It's a very, very long name. But yeah, so TEP 取り戻しをしてんだもんね。
一度、once TEPCO borrowed a lot of money from NDF, and TEPCO plan to return the money in step by step. Yeah.
Mm-hmm. So it means that it's not on the TEPCO side. Excuse me. Yeah. Sorry, there is a complement.
Yeah. So let me clarify briefly. So before the accident, if it's applied to all the nuclear operator in Japan, there is a legislation on such. We need to yearly accumulate or pay the future decommissioning cost to the national funding or national or independent funding account. That has been legislated, and all the operator obeyed the requirement. So we annually paid and accumulated the future decommissioning costs. That's the what has been described before the accident. And after the accident, so what is specifically applied to Fukushima Daiichi Fukushima Daiichi power plant case, as Mr. Kashiwaya and as Yamakami started explaining. So we are now the special counterpart, advisor and supervisor, NDF. So the NDF supervise and inspect our financial status, so on. So annually we have to be clarify what will be the next year's cost we need to use, and so it's a little bit complicated. We pay the amount. And after the review, that's also maybe what we pay is larger than what maybe sometimes we need to pay a little bit larger, not only for next year's expense, but also 2 years, 3 years later's case beforehand. If such a case is, but anyway, we pay the amount we need to use earlier to the NDF, and NDF after review they admit the expense amount, and they pay again to TEPCO. For that, we can invest such a amount of money for any work at Fukushima Daiichi next year and 2 years later and so
on. Thank you very much. That was very clear. So we can continue to the second question about whether TEPCO has plans for economic revitalization of the areas affected by the accident. Maybe colleagues, Mr. Yamakami could cover that.
Yes, in terms of the revitalization of the Fukushima area, that's a very big challenge, and what we need to what we are working hard on it, and so we try to support the local regions in multiple ways, like. For instance, we are trying to we are planning how we can utilize more of the local supply chain companies, or we try to promote the local Fukushima products, and support the farmers or fishermen or industries, and yeah, and we are also planning on how we can develop the capability for the decommissioning in local area, so that the people with the capable skills can grow, I should say. So how we can train the people and improve the capability in Fukushima area. So those kind of plannings are underway. So I hope that answers the question.
Thank you very much. Please let us know if this answers the question. I think it was good introduction to the remediation of the area. We have another question that is focused on the new nuclear program in Japan after the change in nuclear policy that you were mentioning, the one from 2025. How about SMR and AMR, advanced modular reactor, and in particular the fast reactor program? How about closing the fuel cycle in the light water reactors and then in fast reactors?
Yeah, I think many of the plan to R&D for the SMRs and new type of reactors is ongoing by the supply chains and so on, and also in terms of the fuel reprocessing, the Lokkasho is trying to start working on trying to operate. So as explained in the Mr. Kashiwaya's presentation, so at this point, the policy of Japanese nuclear is to maintain a certain level of ratio in the Japanese power generation. So roughly 20% of the energy generation. So that means restarting the existing. It's not only restarting the existing plant, but investing into the new type plant is also opportunity, I think.
Thank you. So we are looking at roughly 20% of nuclear in the Japanese energy system. Thank you. There is a nice suggestion from Mr. Trevor Stocky to ENS, and we keep it as a suggestion. Thank you very much. And we continue with a technical question. What is estimated temperature of the debris itself right now? Is this value known? Is any of the experts here in the room happy to give any light on that? It may also be that we do not have the answer.
大体20から25度で抑えられてます。
So do you mean the contain temperature of the fuel debris at this?
Yes. Yes.
Sorry. We do not have such a data, but we always keep the core of a reactor between 20 to 35 degrees. I hope it's become
So the reactor core is cooled, continuously cooled. So into 25 to 35 degrees. So hopefully, I mean, and the fuel debris are maintaining that level of temperature.
The temperature in the containment and even in the water in the containment is measured, even with the water what comes out. So this information is available. You can find it on the homepage on TEPCO, what is the current temperature. But it means we don't know really what is inside the core melt, but it should be close to that due to the way when it's spread.
Thank you. So we have the indirect, but we do not have the direct.
Yep.
Thank you. We are taking last questions that are already in the chat. There is a question about the sharing the liabilities. So the Japanese state assumed the largest share of the remediation costs after the accident. The question is if there were discussions on how to distribute or share liabilities, so this responsibility for the costs in the future. And I imagine that it may be also a general question. We do not have an insurance expert here in the room, but is there any answer that you would like to provide to this question?
Liability. Sorry, you mean the compensation to the public?
The costs of remediation.
So most of the compensation cost and for the revitalization and so on, that's something what TEPCO needs to, pay for the to accomplish the revitalization. That's our responsibilities. で、8兆円ってなんだ
We can also move to the next question, and if there is, if you want to take time to reflect on this one, the next one is focused on the situation in the originally evacuated area. Are there any areas where people cannot return? And how have evacuated people been compensated? I think we can show a map of the currently evacuated areas. Uwe, do you want to walk us through it?
It's more, so explain, I tried to put which together. On the left side, this was the situation in April 2011, where we have the 20-kilometer zone, which was evacuated. The green was areas prepared for evacuation, and the yellow one was planned evacuation zone. And in comparison, on the right side, this is the situation today. What is you can see all what is green. I'm not sure it's so visible. What is green? This is a return area where the people can go back. It's currently working on other areas to prepare for return. And the red one is called the difficult to return zone, and is currently evacuated until now. It's a lot of work is done, and it's done further for reduce radioactivity. And we have to keep in mind that the radioactivity naturally reduces due to the fact that the half-time of most of these elements are less than some years. So a lot of area is now open for the people to go in. It's sometimes I call it's now a touristic hotspot to have a look on Fukushima, because when you come from Tokyo, so you come from the south, you come practical, you can see the plant. No? It's no more restricted on that. So there's a lot of success, but nevertheless, there's a lot of things to do from an external view, not TEPCO.
So let's maybe finish this topic to TEPCO colleagues. How have the evacuated people been compensated for the evacuation?
Yes, the compensation to the people who evacuated from the area is being continued, and TEPCO supports that, pay the compensation and support the people who are suffering from those events. Yes.
Okay, thank you. There is a question from Samuel Kitchen asking about what is the future of the Fukushima site. So in UK, there was an incident at Sellafield site, which has become later the facility for the processing of waste and decommissioning or cleanup. Is there any plan for Fukushima Daiichi to become something similar, or what will be the future of the site?
It's a very difficult question, but the answer is still being considered, and there's no fixed plan for how the plant should look like at the end. So we are currently trying to develop a long-term plan for the site, whether that should be to consider the end state, what we are calling, whether it should be a fully decommissioned site or repurposing it into a different facility or so on. That planning is still being continued. So yeah, maybe like, and that's not something TEPCO can only TEPCO can decide, but there's a very sensitive topic that local people may feel that they want to become a green field and become a area which they can live again, but other government might say different things. So it's not. We have to continue the conversation between all the stakeholders to come up with that plan. Yeah.
Thank you. So this is the decision is the matter of the future, and multiple stakeholders, as you mentioned, need to meet their needs somehow with this. So we are waiting for the news about this in the future. We have 2 remaining questions, and I would just request that we answer them shortly. And comment from me, the slides, we will need to approve with the speakers whether the slides can be shared after session. If this is approved by the 2 companies, then we will certainly share them with the participants. So question number 1, could you explain how IAEA safeguards inspections are being carried out at Fukushima Daiichi? So IAEA inspections, what is happening right now for the Fukushima site?
So yes, the IAEA has been involved in the we've been engaging with IAEA to in many aspects about, for example, as Kashiwaya-san mentioned about the discharge of the treated water. Yeah, and so we comply with what IAEA expect, and so we follow the international standards in every decommissioning activities. So
and two IAEA members have been staying at Fukushima Daiichi nuclear power station, and they always inspect our facilities regarding ALPS treatment water discharge.
Thank you. So ongoing inspections are an everyday thing for you. Thank you. And finally, this will be our last question today. Was there a modelization, a simulation performed for the Deck B design extension studies for the spent fuel pools following the Fukushima accident? Would the results be publicly available? Where?
I really could say I don't know about this one. I know about tests and system installed for cooling the fuel by spraying. So this type of accident analysis were made to prepare that you lost the cooling, you lost the water in the fuel pool. But I'm not aware of any studies that they really looked on core melt in the fuel pool. That was what I like more to prepared, not to let's come to core melt or fuel melt and to avoid the fuel melt. But maybe but I don't know.
Thank you. In case there is an awareness of such study also among the participants, you can share in the comments. And I will just precise here that the IAEA question was really focused on the accountancy for the nuclear material. So we are looking at the safeguards, inspections, and accountancy for the fuel material that was probably displaced, and its mass was changed, its location. Mr. Ihara, maybe you want to complement to that.
Yeah, so that's a safeguard issue. Safeguard issue is only dedicated to Department of National Regulator NRA, and typical response and requirement is specifically communicated to it. And what's going on, so the new requirement, which part, and TEPCO doing blah, 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 such information dissemination just to make our facility vulnerable. So I think that we cannot answer to that question, but the safeguard issue, of course, IAEA is very basic role, and they practice to all the national competent authority, and each nuclear operator is applied 24/7. So yeah, we are responding well, but specific what's going on safeguard activity is we cannot answer. Thank you.
Thank you very much. I would like to thank the speakers, the colleagues who supported the answering of the questions, and to all the participants who came to our webinar and asked those interesting questions. We will again share the information about whether the approval is given for sharing the presentations, and I wish you a good continuation on the day wherever you are located. Thank you very much.